This is Mrs. O'Neill for Chapter 6, Section 3, Part 2, Ions and Ionization Energy. Pause the video, fill in the blanks, and then play to hear my words. Remember to read as you write. So first, ionization energy is the amount of energy needed to remove an electron from an atom. So we had take an atom, how much energy is needed to remove that electron, and that's how much ionization energy there is. I want to remind you that the only element that only has one electron is hydrogen. So that's why we call this first ionization energy. We're going to talk about the second and third ionization energies when we have more than one electron to be removed. So again, going through those trends. Down a group, the trend is going to decrease. Our ionization energy is going to get smaller. Why? Because those valence electrons are going to be farther away from the nucleus. If those valence electrons are farther away, they're going to be easier to be removed, and that's why the amount of energy would be less. Now let's think about across the period. The amount of energy needed to remove those electrons are going to be higher. Why? Again, you have more valence electrons, you have more of that Coulombic attraction, you have that force that's going to be stronger between those electrons and that nuclei because of the protons that are positive inside. And again, you get more stable. As you add those valence electrons, you're going to become more stable, and it's going to be harder to remove those outside electrons. So again, if we think about the size of the atom getting bigger as we go down, think about how many valence electrons group 1 has. 1, 1, 1, 1, 1. However, hydrogen has it in the first energy level, lithium has it in the second, sodium has it in the third, and so on. So as our size gets bigger, our valence electron is going to be farther away. So the amount of energy needed to remove the one valence electron from rubidium is going to be a lot easier, so less energy than it is from hydrogen. So now let's think of it this way. Now let's go across that period again. So sodium has only one electron, right? So sodium has one electron, magnesium has two. So again, the atom wants more electrons, right? So sometimes the more electrons it has, it's not going to want to give it away. It's going to want it. And that's what's going to happen here. So groups 1 and 2 have 1 and 2 valence electrons. So now let's look at group 13 has 3. 14 has 4, 15 has 5, sulfur group 16 has 6, chlorine is going to be group 17, 7 valence electrons, and of course argon has 8. So again, as you increase the amount of valence electrons, really the amount of energy needed to remove is going to be so great because number one, the size is smaller, so that Coulombic attraction is stronger, but also because it becomes more stable. So we want to remember that argon already has 8 valence electrons. That's what elements want. So it's going to be, takes a lot of energy to remove those electrons. So hopefully that makes sense. So again, let's look at the graph. Let's look at, or let's focus on the groups. So we're going to have I believe that's hydrogen, right? So hydrogen to lithium, to potassium, to rubidium, and then all the way down here, I believe, is cesium. So what's happening as we go down the group, the energy needed to remove that valence electron is going to be less. So again, those electrons are farther away, which means there's less attracted to that positive nucleus. Remember that bigger the atom is going to be easier to take away those electrons. Okay, again, with this group, with this graph, now let's think about those periods. So here's period 1, period 2, period 3, and period 4. So again, let's think about what's happening here. There are more valence electrons, right? Because group number equals valence electrons. So now you're going to have more attraction to that nucleus, meaning that atom is going to be smaller. So it's going to be harder to take away that electron. And if it's harder to take away that electron, you're going to need more energy to do it. So again, pause the video, looking at that graph again, see if you can answer A, B, and C. Hopefully you paused the video and came up with those answers, and hopefully that makes sense. So again, our trends in ionization energy are, as we go down, it gets smaller, and as we go across, it gets larger. So which element would have a larger first ionization energy? An alkali metal in period 2 or an alkaline metal in period 4? So again, we're going down. So is it going to be period 2's element or period 4's element? Hopefully you came up with period 2 would have a larger first ionization energy. So let's look at this chart. This chart gives us first, second, and third ionization energies. So if we look at that first ionization energy and the amount that it takes for the second, what am I talking about here? First energy, second ionized energy. So what does this really mean? Like I said before, it really talks about the energy needed to remove that second electron. So we want to remember that hydrogen is the only element that only has one electron. Every other element has multiple electrons. So how much energy is needed to remove the second versus how much energy is needed to remove the third electron? So I believe you need to pause and write that information down. So if we look at an element like, let's say, chlorine, chlorine has 17 electrons. So it technically would have 17 ionization energies. How much energy is needed to remove each of those electrons? Now remember though, it's going to happen one by one. You have to remove the first one, then the second one, then the third one. You're not going to be able to remove all 17 at one shot. So let's take a look at the ionization energy for lithium. And let's look at the first versus the second. Oh my goodness, right? We're going from 520 to 7,000. Well, let's look at that lithium atom. Now hold off on drawing anything because I know you have to draw it in your notes, but let's look at this lithium atom. And remember, it has one valence electron. So that one valence electron is going to be removed, and now it's going to become an ion. So what happens? Why is it so much to take that second one away? Well, after removing the first valence electron, I spelled valence wrong. The second one now becomes our core electron. That's why we talked about valence and core electrons before. So that core electron is an inner, it's on the inside energy level. It's going to take an extreme amount of energy in order to remove a core. So valence electrons are easier than core electrons to be removed. Okay, so now let's take a look at beryllium. Okay, again, we have 1, 2, 3. We have 3 ionization energies. We go from about 900 to almost 2,000 to, oh my goodness, 15,000 joules of energy in order to remove that. Okay, so again, here we have beryllium. Again, hold off on drawing. So what happens is it's going to take away 1, 2 valence electrons. Okay, so the first valence electron is going to take about 900 joules of energy, and then kilojoules. Your second electron is going to be about 2,000. But so if we think about this, the third electron is going to be on that inside. Those are going to be our core. So removing the first valence electron is not too bad, but it's going to be able to remove another valence electron before removing that third core electron, and that's going to take a heck of a lot more energy substantially to go through that. So make sure to make those drawings in there and some kind of explanation so you understand first ionization energy versus second versus third, and understanding valence electrons are easier to be removed than core electrons. Remove, there we go. Yeah, electron in the inner energy level. Okay, so how do ions form? Well, positive ions are going to be formed because electrons are lost in an atom, and negative ions are going to be formed because electrons are gained in that atom. So ions just means an atom that has a charge. So cations are positive. Those are going to be your metals, and they lose electrons. Anions are going to be your negatively charged ions. Those are the non-metals, and they're going to gain electrons. So I always like to remember that cation is positive, and it has like a plus sign in it, so it's positive. So again, let's look at these positive ions. What happens is an electron is lost and now becomes a sodium ion. Okay, so what happened to its size? Notice, It actually decreased in size. It got smaller. Well, that should make sense. If I'm losing something, I should get smaller. Now, what happens when a sodium atom loses an electrons and now it becomes positively charged? What happens to the protons and neutrons? Nothing. All right, protons and neutrons never change when we're dealing with ions. How about negative ions? What's going to happen is that it's going to gain an electron. So now the chlorine atom has now become the chloride ion. Notice there's a name change, and we're going to be more specific about that in the next chapter. We're going to talk about how these endings change. So what happened to its size? Well, negative ions are going to be bigger. Well, that should make sense. If I'm gaining something, I better get bigger. So again, what happens to the protons and neutrons during these changes? Absolutely nothing, okay? Ions, or I should say electrons, are the only things affected when we're talking about ions. Okay, so again, metals are cations. They get smaller because they lose electrons. Anions are your non-metal ions, and they get larger because they gained electrons. And again, I give you this nice visual between the group 1 alkali metals and the group 17 halogen nonmetals. So then the ionic size, this should make sense, right? The size of the ion is going to be compared to that atom it came from. So pause the video, make sure that you read that information because I just went over it. So again, trends in ionic size, again, going down, it's going to increase, but for cations, it's going to decrease and then get large again and decrease again. So it kind of makes sense there, but maybe it doesn't at the same time. So again, I'm going to show you this. This hopefully makes a little bit easier understanding. Again, as we're going across the period, we start out with pretty big getting small and then really big getting small again because of the atom that it came from. So let's look at these practice problems. So make sure that you have your real periodic table out. Again, I have a reference here, and I'll do one or two together, and then you can try on your own. So it says, out of these pairs, which one's going to have the smaller ionization energy? So pause and see if you can find potassium and copper. Hopefully you found them there. So they're in the same period. And as we go across the period, ionization energy increases. So your answer should be potassium is going to be the smaller of the two. All right, letter B, find copper and bromine. I found them here. Copper and bromine again are in the same period, and as we go across it gets larger. So again, copper is going to have the smaller ionization energy. All right, do letter C and D. So for C, you should have found those two elements there in the same group. So osmium is going to be your smaller ionization energy, and cesium and lithium are also in the same group. So cesium is going to have the smaller ionization energy. Okay, going the other way, larger. So again, I'll do silver and gold with you. There they are on the periodic table. Going down the group, it gets smaller, so silver is going to be your answer. So again, do B, C, and D. B, right there's the elements. F is your answer. For letter C, there's your elements, and fluorine again is your answer. And for D, sulfur is your answer. So hopefully that makes sense. All right, how about if I give you atoms versus ions? Which one's going to be smaller? Here's a nice visual for you, hopefully. So we have our sodium atom turned to ion, and here we have a chlorine atom turned to ion. So out of A, which one's going to be smaller? Hopefully you decided on lithium. Okay, do B, C, and D. So you should have gotten that, that, and that. Notice your more positive particle is going to be smaller. So obviously the other way for larger. And again, there's a visual to help you. So for letter A should be your more negative. B, same thing, and C. Carbon, C for letter D. Okay, so hopefully that makes sense. Another quickie quiz here. Hopefully you paused, you went back into your notes, and hopefully that makes sense. Metals lose electrons and they form cations. All right, we will see you in class.